Welcome to Chapter 3, Section 5, Solving Nth Order, Non-Homogeneous Differential Equations with Constant Coefficients. Actually, this is Part 1. We are going to do the meaning of undetermined coefficients for solving these nth order differential equations. So, here is an example of an nth order differential equation, starting with a derivative of n and a constant coefficient, all the way down to the function of x and its coefficient. Now it's equal to some function over here of x, or some function of the independent variable. It's different. Before we had 0. So the first step in solving these non-homogeneous differential equations is we have to solve the homogeneous ones. Alright, so we call the solution to the homogeneous equation the complementary solution, and we use the variable y sub c to represent that solution. We call the solution of the non-homogeneous equation the particular solution, and we use yp to represent that solution. And then if you use the principle of superposition, which says that the sum of a complementary and a particular solution is also a solution for the non-homogeneous differential equation. So the total solution should be the complementary solution plus your particular solution. So how are we going to solve these? Well, first step, again, is you have to solve the homogeneous equation first. Once you have that, your second step is to make a guess for the particular solution using the function f of x as a guide. The guess needs to be the most general form of f of x with unknown coefficients. So if f of x is equal to x, say, then the most general linear equation is ax plus b. And the third step is to make sure that no terms in the particular solution are duplicates of terms in the complementary solution. If a duplicate term shows up in the particular solution, you must multiply by a factor of the independent variable until all duplicate terms are eliminated, which could require multiple multiplications of the independent variable. So the best way to learn this method is by example. So starting with problem 1 on page 195, we're going to solve this derivative. The second derivative of y plus 16 times y has to equal e to the power of 3x. So it's a non-homogeneous. So our first step is to solve the homogeneous ones, and you should be familiar with this by now. So we need to find our complementary, we need to find our characteristic equation. In this case, it's r squared plus 16 equals 0, and we need to solve for our roots of this equation. And if you solve for the roots of this equation, you find out it's imaginary. It's plus or minus 4i. So if it's an imaginary root, then our solution to the homogeneous equation, or our complementary solution, has to be in this form. Now, we've got that form. Now we need to make a guess. Now, what guess am I going to use? Well, I'm going to use our function f of x. And in this problem, it's e to the 3x. But my most general term of this is e to the 3x is just multiplied times a constant, and I'm going to call it constant a in this case. That would be the most general representation of e to the 3x. We don't have any other terms, any other polynomials. If the polynomial was larger, then we'd have to replicate that polynomial. So now what we do is we check to see if this is going to solve our differential equation over here. To do that, I need the second derivative of my solution and then my solution again. So to find the second derivative, I've got to find the first derivative first. And then once I have the first derivative, I have a second derivative. Now I'm going to plug it back into my differential equation. So I plug in my value of my second derivative, plus 16 times my function of y. I can factor out an x, e to the 3x program, and we find out that now the trick is we have coefficients. I have a coefficient here of 25a and a coefficient here of 1. So this has to be equal, so I have to make these coefficients equal. The only way I can do that is a has to be 1 divided by 25. So my particular solution is 1 over 25 times e to the 3x. And so my actual solution will be the complementary solution plus my particular solution, which would be this. Now, if I had some initial conditions for this problem, I could plug them in and find the coefficients C1 and C2. And that's how you apply the method of undetermined coefficients. Since I do not know these coefficients A, that's my undetermined coefficient for this problem. So let's try another example. So here's a fourth order differential equation. So I need to solve my homogeneous one first, and if I do that, I get the characteristic equation of this form. I need to find the roots of that, and if you do that, you'll find that is a root, and so I'm going to get 4 roots. I get 2 repeated roots of -1 and a repeated root of 1. So that's going to require my solution to be of this form. So here's the root for r equals 1 there. Here's another root for r equals 1, but I have to multiply by one independent variable. And then here's my root for r equals -1. And then here's my second root for r equals -1 and multiplied by another independent variable. So let's find the characteristic or the particular solution now. Now you see here my function f of x is a polynomial of order of the first order, or of n equals 1. So I choose this polynomial with unknown coefficients a and b, and then if I multiply it times my e to the x, I have my guess for my particular solution. Now if I look at this, this particular solution duplicates the solution to the homogeneous equation down here. I got a constant times e to the x, I got a constant here times e to the x, I've got a constant here times x e to the x, I got a constant here times x times e to the x. This is a duplication, so our solutions still have to be linearly independent. So what I'm going to do is multiply by a factor of my independent variable. If I do that, I get ax squared times bx, but see, the bx times e to the x duplicates this one, so that's not enough independent variables, so I have to multiply by another form of the independent variable. And if I do this, this removes any part of the complementary solution from our particular solution. So my particular solution guess for this case is this one right here. So now I got to plug it back into my differential equations. Well, I got to know the first derivative, and so if you take the first derivative, you get that. I'm going to group my terms together. It's just going to be easier in the end if you regroup our terms together to take the. Now I got to take the second derivative, which is that, and then I'm going to group my terms together again. So that's my second derivative right there, and then I got to take my third derivative. And my third derivative looks like that. And I'm not showing you how I got the derivative this time. I believe you guys can take derivatives, so you can verify my work if you like. And then I have to take the fourth derivative. If you do that, you'll get an expression like that. And now what I have to do is plug it back into my differential equation. So by definition, I have the fourth derivative minus 2 times my second derivative, which is this term right here. So that's 2 times that. And then plus 2 times my solution, my particular solution, which will be that. Sorry, not 2 times, just the particular solution. So if I plug them all in here and then add them together, I get this expression. So I got a constant here. And so let's make sure we understand this is a linear function of the first order of x, but you could also think about it that this is a constant of 0 times e to the x. So I have this polynomial here. So here's my x, e to the x term. Here's my e to the x term. And so what the idea here is we got to make the coefficients equal. So I have a coefficient here in front of the left-hand side, which is 24 times a, and then I have a coefficient right here, which is actually 1 times the e to the x e to the x on the right-hand side. And so I get this equation from that. I do the same thing for just the e to the x term. I have this coefficient right here on the left-hand side, and I have this coefficient on the right-hand side. So I have 2 equations and 2 unknowns. I should be able to solve this system. I can find that a is equal to 1 over 25. And then if I plug that into my second equation right here, I get this equation. And then I'll find that b is equal to a minus 1/8. And then if I plug that back into the particular equation, this would be my solution for the particular solution for the non-homogeneous part. And then I have to add that to my complementary solution. Notice how the complementary solution does not get reproduced by the particular solution. And we have solved a fourth order differential equation using undetermined coefficients. Alright, let's do one more example here. So let's look at problem 19. It's a fifth order differential equation. So I got to solve the homogeneous one. When I do that, I get this characteristic equation. You can see that I can factor out an r squared. And so I'll have 2 roots where r equals 0. And then I have this cubic equation I have to solve. When you solve that one, you're going to get 5 roots. 2 are 0. 1 is real. And 2 are imaginary. So I would get, okay, so if r is 0, I get a constant, C1. Well, the second r is 0 is a constant, but then I have to multiply a factor of my independent variable. And then I got my first real root here, and then I got my imaginary roots here. So we need to predict a particular solution now for our guess. And if we look up here, f of x is a polynomial of second order. So I choose a general polynomial of second order. Down here is my first guess. Now when I check with my complementary solution, I have some solutions that appear in the complementary solution. I have a constant. I have some constant times x. So that shows up right here. So we have to eliminate that by multiplying by enough factors of the independent variable to get any part of the complementary solutions out of the particular solution. So I would have to multiply by x squared to do that this time. And so my particular solution is of this form. Now what I have to do is plug that back into my differential equation. So to do that, I need my first derivative. I need my second derivative. I need my third derivative. I need my fourth derivative. And I need my fifth derivative. It just lets out here that your fifth derivative is 0. Now I got to plug it back to the differential equation. So if I do that, I got 2 times my second derivative. I get 2 times my third derivative. And I add that to 0 I add that to my fifth derivative, which is 0. So when you add all these up, I get this expression. So again, I have to make sure that the coefficients in front of x squared equal the coefficients in front of x here on the right hand side. The coefficient in front of x on the left-hand side has to equal the coefficient in front of x on the right-hand side. Of course, there's no coefficient for x on the right-hand side, so the coefficient has to be 0. And my constants on the left-hand side have to equal my constants on the right-hand side. So if I do that, I get 3 equations with 3 unknowns. And from that, I can get, for the first one is easy. A should be equal 3 divided by 24. I can plug the A back into my second equation here, and I get this equation. And from that, I find out that B is equal to negative 1/2. And then I can plug B in to my third equation. And from that, I get that C is equal to 5/4. Now, what I can do is plug those back into my particular equation that I've got down here. And this is the solution for the particular equation of my differential equation. And I can now add that to my complementary equation to get my full solution for this differential equation, which is of this form. Wow. Yes, these take a lot of work to get done. So it's basically you got to practice, group everything together to make using your doing derivatives easier, and then just adding them all up. So let's do one more. Let's do problem 17 because I want you to show how to handle sines and cosines. So this is our derivative, problem 17. So I have to solve the homogeneous one first. To do that, I get this characteristic equation. This characteristic equation tells me that my roots to that is plus or minus I, which gives us a solution of sine plus cosine times constant each. If you look, alright, so now I need to pick out my particular solution. So if you look at f of x up here, it's got a sine term just by itself, and we got a cosine term times x. Now, the trick's with sines and cosines. If a sine shows up, you have to include this other cosine with it. You can't just do sine. So if the sine shows up by itself, you have to include cosine. If cosine shows up by itself, you have to include sine. So here, I got a constant times sine, a constant times cosine, a constant times x sine because I got an x cosine up here, and a constant times x cosine because I got a constant cosine up here. So I have basically a polynomial of order 1 times sine and a polynomial of order 1 times cosine if you group the cosines together and factor out the polynomial, because technically I have a polynomial of 0th order here and a polynomial of order 1 here. Alright, so now I've got to plug this back into my differential equation. But the problem is, you can't do that yet. The problem is that, look, this sine term shows up in the complementary solution. The cosine term shows up in the complementary solution. So I have to multiply by a factor of an independent variable to change everything. So if I do that, this is what I get for the correct particular solution that I do. I should give you a hint. If you are solving these equations and you choose a particular solution, you get down to the end and find the coefficients, and you find out that there's a discrepancy in what you're solving for, it usually means that you've picked the wrong particular solution. So you might want to come back to here and check, make sure you chose the right terms here. So remember, sine and cosine show up here, so I can't have sine and cosine alone here. So I have to multiply by x. Now, this one does not have any terms of sine and cosine by themselves, just times a constant. This is all, you've got sine x, sine x squared, cosine x squared. So these functions are really independent of the complementary solution. Alright, so we're continuing the solution to number 17. So this is our particular solution. So I need to get its second derivative. So I have to take its first derivative, and then I can find its second derivative. And then what I need to do is add its second derivative and the first derivative together, and if I do that, I get this expression. So I have a coefficient. Okay, so we have a coefficient here times sine, and I have a coefficient here times sine. I have a coefficient here times cosine. I have a coefficient here times cosine. So if we look over here, let's do the sine terms first. So if we look over here, there is no x term on the right-hand side. So that means minus 4e has to equal 0. And then minus 2b plus 2d has to equal 1. So if we find out that means e equals 0, and then 2b equals 1 minus 2d. Now let's look at cosine. Now for cosine term, we do have an x term here, so that means 4d has to equal 1, but we don't have any constant times a cosine. Here's a constant right here, so that means 2a plus 2e has to equal 0. So it's easy to tell me that d has got to equal to 1/4. And if you solve this idea, you get a equals minus e, but we already know e is 0, so a has to equal 0. So now I can take this d to the 4th and plug it back in to here. D to the 4th times 2, or d to the 1/4, sorry, 1/4 times 2 is 1/2. 1/2 minus 1 is 1/2. Divided by 2 is 1/4. So b has to equal 1/4. So we have our complementary solution here. Now I can add my particular solution to it, because we know a is 0, so there's no x times sine. We know b is not 0, it's 1/4, so I've got it right here. I know d is 1/4, so I put it down here, but my e is 0, so that doesn't show up over here. Alright, so that's the solution to non-homogeneous differential equations with constant coefficients. I'll see you in class.